Hi, welcome back. This is week 3 of our videos. Some announcements. It is exam week, so our first exam is going to be on the 8th during your class time, so that's Wednesday. This should be up Monday, so you'll have some time to get some studying in, not with these videos. And I will be holding some drop-in hours the night before the exam, from 6:30 to 8:30 p.m. in cell 214. So that'll be time to ask questions. I'll have some exam prep ready for you guys, some questions, but just come ask questions. So yeah, but today we're going to be talking about finding the electric field due to an infinite sheet of charge. So yeah, let's get right into it. So I have this sheet, and right now it doesn't look infinite, but just imagine that this stretches for forever. It goes in all directions. And we can say that it has a charge sigma. So that's generally what we use for surface charge density, which is sigma, which is what I went over last week, was the different densities that we have. So generally we say surface charge density is sigma. So we want to find the electric field due to an infinite sheet of charge, which is sigma. And this is distributed evenly throughout the entire sheet. So yeah, let's just get right into it. You guys should have been worked on this on Monday in your discussion groups. So hopefully this is just a refresher, but the second video that we're going to go over is what happens when you have two sheets of charge. So that's what we're going to be going over this week. So the first thing I'm going to do, if I want to find the E field of this, is I want to think about Gauss's law. So if we remember, Gauss's law is E dot dA equals Q enclosed over epsilon naught. So the first thing that we should really be thinking about is our Gaussian surface to integrate over. So there are a few different options that we can use in a second, but I'm going to draw a few different ones and we can go through each one and say why it's correct or incorrect. So I have 4 Gaussian surfaces here, and we want to decide which one would be best to enclose a small section of charge so that we can integrate over it to find our E field of this entire infinite plane that has a surface charge density sigma. So the number 1 is just a cylinder that's straight up and down. Number 2 is a rectangular prism, or some call it a Gaussian pillbox. Not sure where that comes from, but yeah, so that's just like a Gaussian pillbox. Number 3 is a cylinder. This is poorly drawn, I'm sorry, but it's a cylinder, but it's just on its side instead. So the circular part is kind of in line with the plane. And then number 4 is just a sphere. So we want to decide what Gaussian surface would be best to solve for the electric field from an infinite plane. So the first thing that we want to remember, and if you don't remember this, kind of go back to Gauss's law video last time. The most important thing is that we want our E and our dA to be in the same direction. So to make sure that they're in the same direction, let's draw kind of what the dA vector would look like on each of these surfaces. So I'm going to take purple. So number 1, the first one has the dA vector kind of up on top like that. And then on the side, it kind of looks like that. And then there's one on the bottom like that. So on each different surface, there's a different dA vector. So, and you can imagine on the first one, since it's kind of spherically shaped, you can imagine that they're all kind of pointing radially outward from the surface. Number 2 kind of has one that's straight up and down, just like this. There's another one like that, like that. Similarly on the bottom, there's ones that repeat like that, and there's also one that goes down like that. Number 3 kind of has something weird going on. Since it's kind of spherically on the top, the dA vectors kind of point radially outward, and then this one has a dA vector that kind of points in the same line as the infinite sheet. And then 4 has kind of dA vectors that go kind of radially outward like this. So yeah. And so we want to find one that would be the best way to solve this. So I should mention that this sigma, we're going to say is a positive sigma. So when it's just sigma, we normally just say that we kind of just assume that it's positive, but I'll make the distinction here that it's a positive. So with an infinite sheet, just like a point charge, the electric field lines will flow from positive to negative, or from positive just outwardly. So we can imagine, I'll do this in blue, that the electric field lines kind of are look something like this. They kind of are just from any point on the surface, and they just flow upwardly. And these are all, since it's the surface charge density and it's uniform, that means that they're all going to be the same, no matter where we take our surface to be, no matter what. So if we can move it, we can move the infinite plane wherever we want, but the electric field lines will all be the same, and the same magnitude as well, since it has a uniform surface charge density sigma. So we want to find a Gaussian surface that matches matches the direction of our electric field. So I'm going to say that this is our E field in that blue. And the purple, I guess I could have done a better job with different colors. Let's just keep it. So let's think about number 3 first, because I feel like that's kind of the one that would be easiest, or one of the easiest to knock out first, because we have these dA vectors on the top when it's like radially, there's a curved surface. So we can automatically see that since there's a curved surface, the dA vectors will go every which way, and we won't have the dA vector and the E field in the same direction. So I'm going to say that we can automatically cancel out 3, because the dA vector is not going to be in the same direction as the E field. And we won't have any cancellation. And so same thing with 4. Since it's a sphere, the top part of it that I drew the dA vectors on are all pointing out radially. And this may work with a point charge, but with an infinite sheet, it's not going to go in the same direction as this E field, where it's just pointing straight up and down like this. So 4 is already out too, because we can't, the dA vector and the E field are not in the same direction. So that leaves 1 and 2, which are both viable options for us. But we tend to pick one over the other. And here's why. There is no why, I don't know. So 1 and 2 are both viable options, and you could use either one of them. But usually standard practice is using cylinders instead of Gaussian pillboxes, just because physicists really like circles for some reason. We don't really like a lot of harsh edges, so we tend to gravitate towards cylinders and spheres, and we usually like spheres a lot more, but cylinders are our next best option. So I'm going to tell you why 1 is our better option. So 1 has this dA vector right here. I'm going to highlight it instead. So 1 has this dA vector right here that I highlighted that is going in the same direction as our electric field. So that's great. And then on our second surface, which is this kind of like curved edge that like encompasses the cylinder, this one right here, I'm going to use a different color. This one right here is actually perpendicular to the E field. So that's great too, because we don't want to deal with so that dA vector actually cancels out because it's perpendicular to our E field. Even if it's radially pointed outward in any direction, since it is on the since the E field, we can say, kind of points in the Z direction if we want to label our axis kind of like this, then our E field is in the Z direction, and we want our dA vector also in the Z direction. But 2 is also a viable option, but I'm personally going to use 1, just because, again, physicists like to deal with spheres and cylinders instead of harsh boxes and harsh lines. So let's use 1. Okay, so now let's actually solve this guy out. So I drew some more electric field lines because I don't think I kind of got the point across quite as much as to how we're going to solve this. So since this is an infinite sheet and we're going to assume that it has this positive sigma, just like a point charge, how it kind of radiates outwardly, this will have electric field lines pointing upward and pointing downwards. So it is just radiating positive sigma charge. So why it's important is because we also have this little piece down here that we're also going to be dealing with. So we're primarily going to be dealing with this guy right here and this one right here, and like these 2 regions here. But I wanted to kind of draw this out a little bit better so that you can get a better understanding as to what I'm talking about. So we've already decided that this is going to be our Gaussian surface, a nice cylinder with our dA vectors pointing upwards and downwards and then radiating outwards on the kind of curved edges. So now let's define our Q enclosed. So our Q enclosed, if we remember, let's define our sigma first. So sigma we know is Q over A. So let's just keep that in the back of our mind. So now let's solve this. So like I said before, we're primarily interested in the places where the dA vector and the E vector, our E field, are in the same direction. So that's 2 places in this case, which is the top, which is, I'll call this 1, and then down here, which I'll call 3, and let's say that this, like the circular outer region, is region 2. So just by looking at region 2, we know that it's going to be 0. And if you don't understand quite why, kind of just imagine, you can look at the E field vector. It's pointing straight up, or it's pointing straight down, and the dA vector are kind of pointing every way except for up or down. So that when we do dot products, like we do in this case in Gauss's law, perpendicular vectors do not create a dot product. They just become 0. So that is why we don't really care about region 2 in this case. So now let's just look at region 2 or region 1 and 3. So we're going to split this up into two separate sections now. So we have the E.DA on region 1 and E.DA on region 3. So let's do that. So we have E.DA, let's say 1 plus 3 E.DA equals Q enclosed for epsilon naught. So in region 1, we know that E and DA are in the same direction, and also in region 3, E and DA are in the same direction. So automatically that cancels out our dot products. So I'm going to just say that E and DA for region 1 plus E and DA for region 3. So looking at our DAs, since this is a cylinder, we know what the face of that is. Those are just two circles. And we know what the DA, we know what the area of circles are. It's just pi r squared. So, and when we do our integration, E just becomes a constant. So basically what we have here is the electric field times the area of two circles. It's also important to note that the magnitude of the electric field is going to be the same whether you're on the top or the bottom. So really what this is E 2DA of region 1. So the reason why is because we can recognize that the top circle and the bottom circle are the same. So it's just two of those circles with the same electric field. So our electric field becomes a constant, and now we know what our area of a circle is. It's just pi r squared, but we have two of them with the same electric field going through them. So I'm just going to say that we have E times 2 pi r squared. Now let's look at our Q enclosed. So our Q enclosed is, we're just going to be looking at one of the circles, just because it's Q over an area. So we're going to look at one circle, and we know what the area is. That's pi r squared. So we know that our Q enclosed is sigma times pi r squared. So that's just going to be sigma times pi r squared over our epsilon naught that we cannot forget about. Okay, so then we can recognize when we move over our 2 pi r squared, the pi r squares cancel out. So we can do that. And what we are left with is that our electric field of an infinite plane of charge is just sigma over 2 epsilon naught. And that is our final answer. And it points in the z hat direction, if we remember how I defined our coordinates from before. So that is our electric field, and it does not matter what distance you are away. Specifically this part right here, like if we wanted to call this h, it does not matter how far that distance h is, because when we did our integral, we can recognize that the E and the dA in that part of our Gaussian surface went to 0. So it does not matter how far away you are from this infinite plane, you will have the same electric field. So that is our final answer, and we can go to the next video where we're going to put two of these suckers right next to each other and find the electric field there and also the potential. So stay tuned for that.